Okay, our next speaker is Hermann Nicolai from the Albert Einstein Institute in Go, and his title is, on the overhead here, E10 and BKL limit of M theory.
So first of all, I would like to thank the organizers for giving me this opportunity to speak here at this conference. Secondly, I would like to thank them for putting me up in room number E10 at Robinson College. On the same floor as my other favorites, E7, E8, and E9. So in this talk, I want to report on work I've been doing with Thibaut Damour and Marc Hainaut. And this has not yet been published, but I hope it will come out soon. I would also like to acknowledge discussions with Alex Feingold and my PhD student Thomas Fischbacher. Well, I've already commented on one of the unexplained items in my title. The second unexplained item is BKL. Now, BKL is in honor of Belinsky, Khalatnikov, and Lifshitz, who more than 30 years ago succeeded in finding a generic solution of Einstein's field equations near a space-like singularity. So here you have the picture. The singularity occurs at time equals t equals 0, and here then space-time evolves. Now the intuition on which their construction was based is the following. Because the singularity is space-like, there's in some sense almost by definition causal decoupling, and therefore they hypothesized that in some sense spatial gradients should become negligible in comparison to time derivatives as you approach this singularity. So in some sense, what's considered as a disadvantage or drawback in conventional cosmology, namely the horizon problem, is here turned to one's advantage. Now, if this hypothesis is true, the Einstein field equations will drastically simplify as one approaches the singularity. In that case, they should reduce to a superposition of ordinary differential equations, a continuous superposition at each space point. Now, this would then amount to a dimensional reduction of Einstein's theory to one dimension. Now, dimensional reduction would be rather boring, but they discovered something interesting, which is the fact that this hypothesis is not quite true. Now, another intuitive way of thinking about this is in a slightly more modern parlance, is to think of this as you approach this singular surface as a kind of small tension limit, if you think about space-time as some kind of elastic medium. Now, it's known in physics that if you take limits of certain parameters becoming very small, then it sometimes happens that in such limits huge symmetries appear. One example is the large energy limit of the Standard Model. Another example is the small tension limit of string theory that was studied by Gross in 1988. And here also the aim will be to exhibit a larger symmetry as you take this limit. Now, there's a huge literature, a huge body of work on this BKL picture, which I now have to summarize in 2 minutes. So if you want more information, there's a recent review here. So one parameterizes the metric near this surface in the following fashion, where Gaussian coordinate system, where the omegas are spatial one-forms whose time dependence is neglected at first approximation. So all the action is supposed to take place in these exponential factors. One then seeks to construct, and now here I'm using high energy kind of language. This is not the way that general relativists would describe it. So what one seeks is a kind of effective low energy theory for these diagonal metric degrees of freedom, which is assumed then to have the following form. There are 2 terms here, the first of which is what you would obtain by direct dimensional reductions of Einstein's theory to one dimension. Now, it's well known that this is a sigma model, and this kind of sigma model simplifies even further if you just take the diagonal degrees of freedom. So this is essentially describing the action of a massless particle in little d dimensions. And it's also well known that from gravity that this metric, which has nothing to do with the space-time metric, it's a metric in the Wheeler-DeWitt superspace, has Lorentzian signature minus plus plus plus. Just like the Wheeler-DeWitt Hamiltonian is known to have this hyperbolic signature. So this is the first term, and if you just had that term, you would just recover the Kasner solutions. The second term is obtained in some sense. It's an effective potential. It's obtained by integrating out the off-diagonal metric components, like these n's, for example. The spatial inhomogeneities, this is in some sense what the BKL did. Matter fields, form fields, etc. Now, let me just summarize the most important feature here. It just turns out that at least in leading order, this potential can be written as a superposition of terms of the following form. You have exponential potentials with which are where the exponents are linear forms in the betas, and the coefficients in front of these terms are positive for the leading terms for all of these kind of perturbations. There will be sub-leading terms for which this is not true, but the leading terms will all have this form of a sum of Toda-Wall potentials, really. Now, as you approach t equals 0, a further simplification takes place, because then these Toda-Walls, which I've drawn here, they become, in some sense, sharper and sharper, because the betas tend to plus or minus infinity as t goes to 0. So in this limit, one obtains the so-called sharp wall potential. This is what people call the sharp wall approximation, which should get better and better as you take t to 0. Now the Hamiltonian constraint, which you derive from this effective action, which I showed on the previous transparency, then assumes this form here. Now in the sharp wall limit, this potential is either 0 or infinity, just like here. So if it's 0, you just have this equation. It's just a dispersion relation for a free massless relativistic particle. And as I said, you would just recover the Kasner solutions, and the Kasner coefficients are just, in some sense, the momenta. Now, when this particle hits one of these walls, it bounces off, and then you have a reflection. The Kasner coefficients change. It's called a bounce. And the whole process then can be described pictorially in this way. So you have these walls here that are defined by the linear forms appearing in the exponential. So this defines the hyperplane. And here I've chosen the coordinate tau, which is such that tau goes to infinity as t goes to 0, just to make this a little more intuitive. And then the process is as follows. You have a sequence of free Kasner flights, meaning Kasner solution, then there's a collision, then you have some other Kasner solution, and so on. Now, there may be infinitely many collisions, in which case you have chaotic oscillations or BKL, which is the interesting case. Actually, this is what happens when you fall into the singularity of a black hole. You get squashed, but you get squashed in an extremely interesting way. Or otherwise, for example, if you switch on a dilaton, then you have something called AVD, as asymptotically velocity dominated, which means that sufficiently close to t equals 0, the solution is a Kasner solution, but with the Kasner coefficients depending on the space coordinate. Now, the crucial insight for what I'm going to tell you in this talk is that it's not so old, namely it's that the dominant walls form the fundamental Weil chambers of some indefinite Kac-Moody algebra. This is where the connection with Kac-Moody comes in. Now, this has led to some clarification subsequently, namely, first of all, that one can identify this truncated Wheeler-DeWitt superspace with the Cartan subalgebra of this indefinite Kac-Moody algebra in question. And secondly, there's a Kac-Moody theoretic understanding of when chaotic oscillations occur or not. You have chaos when the algebra is hyperbolic, meaning that every subalgebra, regular subalgebra, is either finite or affine, and you will have regular behavior if the algebra is indefinite. So here are two examples, prominent examples. One is pure gravity in d dimensions. Now, here I've also denoted the walls. The symmetry walls are what you get by eliminating off-diagonal metric degrees of freedom. And then this extra element, this is the gravitational BKL wall due to spatial inhomogeneities. And in 11-dimensional supergravity, it's the electric wall. So as I said, this has led to some more systematic understanding of the behavior of the solutions near the singularity. And the one thing I would like to emphasize, and this was discovered by Damour and Ernaud, that all the theories that we're discussing at this conference, namely the type 2a, type 2b, supergravity, 11-dimensional supergravity, they all exhibit chaotic behavior, which I think is extremely significant. Now, I think the fact that these Kac-Moody algebras appear here cannot be an accident. So you wonder, is there more to this, or is this it? I mean, is this just the fact that you have this identification of the Cartan subalgebra with the diagonal metric degrees of freedom? So our goal in this investigation is to extend, to find out whether there's something beyond, and to extend these considerations beyond leading order in this BKL type approximation, and also beyond the Cartan subalgebra. Now here's the main idea of my talk. At this point, still largely conjectural. If you like, you may also call it a vision, but I'll try to make it a little more precise. Now what we're looking for is a map that relates the time evolution of the geometrical M-theory data, which means the fields of t equals 11 supergravity and perhaps something else, and all their spatial gradients to a null geodesic on an infinite dimensional coset space E10 over K-E10. Now this is for M-theory. I should also say that I'm just talking about the bosonic sector, no mention of fermions in this talk. So in spirit, this is somewhat similar to matrix theory, where you also try to describe the dynamics in terms of matrix model, SU infinity matrix model, in terms of quantities that just depend on a time coordinate. But here it's quite different. The other scheme was obtained from Young-Mills. This will be related to supergravity. Now, I would like to recall in this context that already 20 years ago, Julia conjectured the appearance of E10 as in the one-dimensional reduction of d equals 11 supergravity. Now, this is not, I should emphasize, what this is not just a mere dimensional reduction. In some sense, if the procedure works, then this should retain the memory of also the full space dependence of this theory. Now here are the results. First of all, we can construct this map to low orders such a way that the previous Toda wall Hamiltonians that have appeared in this BKL description appear as can be rederived in a sort of very nice group theoretical fashion. And I'm also going to show you that this coset space can indeed accommodate in a more precise sense the geometrical data, meaning these spatial gradients of 11-dimensional supergravity. So here's what the competition is doing, and I have no further comments on that. So let's proceed formally. Now you should understand, at the beginning, these are highly formal constructs. And I will have to tell you how to make these prescriptions a little more operational. Fortunately, all the ingredients that go into the construction of finite dimensional sigma models over finite dimensional groups can be formally extended to this case of indefinite or hyperbolic Kac-Moody algebras. So the basic object of the theory is matrix, if you like, in this coset, which you can think of as a vast generalization of the field line of general relativity with K, the compacts, well, I'm going to define what it is in a moment, of E10 as the analog of the Lorentz group. And also the velocity, which is the logarithmic derivative, which is an element of the Lie algebra. The Lagrangian then can be simply written down in this form. We have a lapse function because we still have invariance with respect to time reparametrization invariance. There's a symmetric part, adding V plus its transpose, that can be defined in this case by means of the so-called Chevalier involution, which is defined in terms of the basic generators of the Lie algebra. And the maximal compact subgroup is defined to be the invariant subgroup under this Chevalier involution. This bracket here, that's the so-called standard bilinear invariant bilinear form of the Kac-Moody algebra exists for indefinite Kac-Moody algebras. It's what becomes the trace in the finite dimensional case. Now, interesting, you may note that in the infinite dimensional case, this is about the only thing we can write down. There are no other polynomial Casimir invariants on E10, so you wouldn't be able to write down a Westermino-Witten term for this. But we note the existence of transcendental invariants. Unfortunately, they are not given very explicitly, but you might think about modifying this by non-perturbative terms. Now, unfortunately, working out this Lagrangian is not as easy as it sounds. And just to illustrate the difficulties, let's have a look at rank 2 Kac-Moody algebras and just increase this off-diagonal entry from 1 to 3. So here everybody knows this, SL3. I guess here everybody knows this too. This is affine SL2 with a root diagram. Now let's increase 2 to 3, and what you get is this. This diagram was worked out by Alex Feingold. It's unpublished work of his, but he has given me permission to show it to you here. I think it beautifully illustrates the difficulties that you get by replacing 2 by 3. So what you see here is, first of all, the simple roots, 2 simple roots. And then in red you see the real roots, now spaced farther and farther apart. And all the black dots are so-called imaginary roots, squaring to numbers less than 0. You see the numbers here, even if you can't read them, doesn't matter. The numbers indicate the root multiplicities, which means the number of independent Lie algebra elements associated with a particular root. So each dot here will already have a billion or so Lie algebra elements associated with it. These numbers are known to increase exponentially, but there's not a single Kac-Moody algebra which they're known in closed form. So how do you come to grips? I mean, we have to do something. How do you slice this monster of a Lie algebra? You have to, there has to be a way to describe in somewhat more simple terms. Now here you see the cone, the forward light cone in root space for this Kac-Moody algebra. The real roots are outside, I haven't drawn them. The null roots are on the cone. And, well, there are various ways of slicing. That's already schoolbook mathematics, either with respect to a hyperbolic subalgebra. This hasn't even been tried for the simple reason that nobody knows that we can't really characterize these algebras. What has been tried is slicing with respect to affine subalgebras, which gives these parabolic sections. Unfortunately, this has only been done up to affine level 2, which means how many layers you can go like this. And after 20 years, I would say that's, we can say that it's fair to say that this approach has gotten stuck, because there's no way, so far no one has figured out how to do this for level 3, 4, 5. So we're going to do something more modest in order to understand the algebra deep inside the light cone. A bottom-up approach by slicing the Lie algebra like this. So let's do this for E10. Means we're going to slice the algebra with respect to this root rather than this root, which would be the one for the affine decomposition. So we decompose it into representations of SL10, or actually rather GL10, because the dual element of this root in the Cartan subalgebra will enlarge SL10 to GL10, and that's precisely the GL10 you see when you reduce 11 dimensions to 1 dimension. Now these irreps are characterized by highest weights, or Dynkin labels, given here. They are positive, non-negative integers, or Young tableaus. Now if you work out the relations between the Dynkin labels and these numbers which appear, you find this following interesting equation, which looks innocent, but it's actually a rather powerful thing. Here's the level. This S is the inverse Cartan matrix of SL10, and the important thing is there's only positive entries. So this equation is rather easy to analyze, because you give a given level, and then you just have to solve this equation. It's a Diophantine equation such that both the m's and the p's are 9 tuples of non-negative integers. For example, for the Feingold-Frankel algebra, it's easy to do this by hand up to very high levels. For E10, well, it's a little more, it's harder work. There's another condition, which tells you that lambda squared, the highest weight must be a root. That's this condition. It essentially takes care of the Serre relations. Some water. Sorry. So finding a completely explicit description of the E10 algebra in terms of infinite towers of GL10 irreps is thus reduced. I mean, this is relatively easy to solve to finding the outer multiplicities, namely the number of times these irreps appear at each level. So at each level you have a stack of GL10 representations, and then you can express the root multiplicities, the things that mathematicians are interested in terms of the weight multiplicities. This is well understood, and this is actually the only unknown for which we don't have a way to compute. So what are the low-level irreps? They're easy to determine. Here they are. And actually I should say that this has already appeared in work by Peter West, and implicitly in this paper, but only for the E8 truncation. Now you see old friends reappearing. There's the 3 form, 6 form, and something else. And clearly you would like to associate this with a graviton, the 3 form field, the 6 form field, etc. So if you've ever wondered if there's a superior reason why you have the 3 form field in 11-dimensional supergravity, here it is. E10 gives you these fields quite naturally, and it's obvious that this should be interpreted as the dual of this. Well, you can also go on further, but I'll tell you about this a little more. So what's the basic correspondence we've established? Well, this is technical. I don't want to go into details. You have 2 things to compare. One is 11-dimensional supergravity, and you write the equations of motion in a way where you split off time derivatives from space derivatives. So this is what's been done here. On the one hand. On the other hand, you, for the sigma model, and this is now, I mean, you really use the concepts which I showed you before. We have these low-level generators, and you just plug them in, work out the bilinear form, etc., and then you find that there's complete matching, at least up to level 3, between the sigma model quantities and the 11-dimensional quantities. I should say that if you were just to do a dimensional reduction, life would stop here. Here we've already taken into account the first spatial gradient, another spatial gradient, and here you also see BKL, because BKL took this to be constant, so this fits in. You also see the wall structures appearing. This is the electric wall, magnetic wall, BKL wall, and then it will go on. So we've done this to this order, but the question is, of course, how would you like to continue? Now, the search for the affine, so just to tell you a little bit about higher derivatives, you can analyze these conditions which I showed you. There will be so-called affine roots defined by this condition, and they reveal the existence of the following infinite tower of E10 elements. I mean, these are genuine Lie algebra elements of E10. So what you see here is essentially the representations of the 3 form, 6 form field and the dual graviton reappear. Now this is distinguished by the fact that if you truncate these indices in a particular fashion, lower ones to be equal 1 and the upper ones in 2 to 10, then you recover precisely the elements of the affine subalgebra E9, including the central term. That's important that it's GL10 and not SL10. Now, as I said, we still have to work out these higher derivative things, but there's one truncation where you compare and which gives you confidence that something is going to work along these lines. Namely, you can compare this with a linear system of 2-dimensional supergravity in 2 dimensions, which is known to possess E9 invariance. Actually, this was already understood 15 years ago. So the association which is suggested by this is this equation. And now here you see, indeed, this has the right structure for all the higher order spatial gradients of these fields and dual fields. In the truncation to 2 dimensions, you just retain one space direction. It's one space plus one time. And then this would just be the nth spatial derivative. We know how that works in the case of the Garrosh group. There's an infinite tower of higher order dual potentials. So what this suggests is that the potential that comes with this is such that its nth derivative, time derivative, is related to this quantity at a certain space-time point. So finally, I want to show you a little more. You can analyze these conditions which I showed you, these here we go, these conditions a little further. And, well, as I said, in order to figure this out, we need to figure out the outer multiplicities. We don't know how to do this at the moment, but we have some formulas. We can use some tables for this. And then, knowing this, we can figure out what this is. So the table we've been using is this one. This is a table of E10 multiplicities, and this is something we computed 4 years ago. I should say that here's the affine level, and for 0, 1, 2 it's known. But the interesting numbers are when you have 3, 4, 5, etc. in here. So what you do is you just take those numbers and match them. This has been done on the computer with my PhD student. By the way, it's a nice check on some of these calculations. So here's another glimpse of E10. What you see here is now the irreps which appear at levels 7, 8, and 9. We also have 10, which I'm not showing that. And now what you see here is these representations which is marked by this cross. Gary is still sitting. These are the ones that come with the higher order spatial gradients. In this case, you'd have the second order spatial gradient. But you see there's a lot of other stuff. And the other thing you see appearing here is now that these outer multiplicities, which were equal to 1 up to level 6, now start increasing, and they will eventually start increasing exponentially. So you now see that there's a lot of other stuff, and it will be interesting the thing I would like to emphasize here is that with this you can really start writing down Lie algebra generators, commutation relations, work out commutators, etc. Work out the sigma model up to this level, and then compare it with 11-dimensional supergravity. And the reason I didn't put D equals 11 supergravity, but M theories, that clearly there's something else here. I don't know what it is. Might also contain higher order corrections in some sense to M theory. So here comes my last transparency. So all of this suggests the existence of a huge and hitherto unknown non-local symmetry of Einstein's theory, or some theory beyond, which sadly transcends Garrosh group in the sense that Garrosh just acts in 1 + 1 dimensions, whereas this will act in more dimensions. So I think this may eventually also have something to say about the problem of constructing observables in general relativity. As we heard yesterday, it's a non-local. You get non-local quantities, so this fits. The other thing I would like to emphasize again, all the theories we're talking about here have this chaotic behavior, which at t equals 0, which I take to mean from this Katz-Moody theoretic interpretation that an approach where you reduce the dynamics just to the time dependence of a few scale factors in describing what's happening at this t equals 0 moment is far too simplistic. So I would like to conclude with a quotation from Shakespeare, and in particular the last part of it I think is a good thing to keep in mind if you're working on M theory cosmology. Thank you.
Do we have some questions, comments? No. I just have one question, which is in 4 dimensions, carrying on the derivative expansion. Has that been very successful?
That hasn't even been tried. We just take so far. Actually, I should say that everything I've talked about here can also be done, and we have done it actually for 4-dimensional gravity, in which case the Katz-Moody algebra is this Feingold-Frankel algebra. And in fact, I think we'll try that first to see whether the procedure works to higher orders.
Are there any more questions, comments? In which case we should break for coffee and return.